1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Keep going. 1/6, 1/7, 1/8. This is the harmonic series, and it does something that feels wrong. If you add up enough terms, the sum passes 100. Add more, it passes a million, a billion. It grows without bound. It diverges to infinity. Slowly, painfully slowly, but it gets there. Now I want you to watch what happens when we make one small change. Go through the series term by term and cross out every fraction whose denominator contains the digit 9. 1/9 is gone. 1/19 is gone. 1/29, 1/91, 1/99, 1/900. Any number with a 9 anywhere in it, erased. What is left? A series that converges to roughly 22.92. That is a finite number. You took a series that was heading toward infinity, removed some terms, and it collapsed into something you could write on a napkin. The question that should bother you is, how? You have not removed that many terms, one digit out of 10. Roughly 10%, you might think. How does removing 10% of a divergent series make it converge? The answer is that you are not removing 10%, and that is the whole story. Before we can understand why removing a digit works, we need to understand why the harmonic series diverges in the first place. Because the divergence is strange. The terms are getting smaller. 1/100 is tiny, 1/1,000,000 is microscopic, and yet the sum keeps growing. The cleanest proof comes from Nicole Oresme, and it is nearly 700 years old. Group the terms. The first group is just 1, and it equals 1. The second group is 1/2, standing alone. The third group is 1/3 plus 1/4. That sum is 7/12, which is greater than 1/2. Fourth group, 1/5 plus 1/6 plus 1/7 plus 1/8. 4 terms. Each of them is at least 1/8, so the group sums to at least 4/8, which is 1/2. Fifth group, 1/9 through 1/16. 8 terms, each at least 1/16, again at least 1/2. See the pattern? Every group sums to at least 1/2, and there are infinitely many groups, so the total is at least 1/2, added up infinitely many times, which is infinity. The harmonic series diverges. Simple and clean, 700 years old, still the standard proof. But the divergence is logarithmic. The partial sums grow like the natural log of n. After 10 terms, the sum is about 2.9. After 1,000 terms, about 7.5. After 1,000,000, about 14.4. Let me give you a number that puts this in perspective. To reach a partial sum of 100, you would need roughly 2.7 times 10 to the 43 terms. That is more terms than there are atoms in the observable universe. The harmonic series diverges, but it takes its time. It is the slowest march to infinity in all of mathematics. And that matters because it means the series is vulnerable. Pull out the right terms and the whole thing collapses. So which terms are we pulling out and why does it work? The answer comes down to counting. Start with the single-digit numbers 1 through 9. How many lack a 9? 8. We lose only the number 9 itself. 8 out of 9 survive. Two-digit numbers 10 through 99. The tens digit can be anything from 1 through 8, so 8 choices. The units digit can be anything from 0 through 8, so 9 choices. 8 times 9 is 72. Out of 92-digit numbers, 72 survive. That is 80%. Three-digit numbers. The hundreds digit has 8 choices, 1 through 8. The tens digit has 9 choices, 0 through 8. The units digit has 9 choices. 8 times 9 times 9 is 648 survivors, out of 900 total. About 72%. The pattern is clear. Among all n-digit numbers, the count that contain no 9 is exactly 8 times 9 to the power n-1. Now here is where it gets interesting. The total count of n-digit numbers is 9 times 10 to the n-1. So the fraction that survive is 8 times 9 to the n-1 divided by 9 times 10 to the n-1. That simplifies to 8/9 times the quantity 9/10 to the n-1. 9/10 is less than 1. And when you raise a number less than 1 to a growing power, it shrinks exponentially. Let me show you how fast. At 1 digit, about 89% of numbers survive. At 5 digits, 53%. At 10 digits, 39%. At 30 digits, 4%. At 50 digits, 0.5%. At 100 digits, 0.003%. Among 100-digit numbers, 99.997% contain at least one 9 somewhere in their decimal expansion. Think about what that means. Almost every large number has a 9 in it. When you cross out denominators containing a 9, you are not removing one term in 10. Among small numbers, sure, the removal is light, but among large numbers, you are removing almost everything. The survivors are a tiny, exponentially shrinking minority, and those survivors are already contributing tiny terms, since each one is the reciprocal of a number with many digits. Few terms, each small. The sum cannot reach infinity. That is the intuition. Kempner turned it into a proof. In 1914, a mathematician named Aubrey Kempner published a 3-page paper in the American Mathematical Monthly. The title was A Curious Convergence Series. 3 pages, and it settled the question completely. Here is the argument, and it uses exactly the counting we just did. Take all the terms in the 9 free harmonic series and group them by the number of digits in the denominator. The first group contains the single-digit terms, the second group contains the 2-digit terms, and so on. For the n-digit group, we already know there are at most 8 times 9 to the n-1 terms. That is the count of n-digit numbers containing no 9. Now, what is the largest any single term in this group can be? Every n-digit number is at least 10 to the n-1. The smallest 3-digit number is 100, which is 10 squared. The smallest 4-digit number is 1000, which is 10 cubed. So every reciprocal in the n-digit group is at most 1 over 10 to the n-1. Multiply the count by the maximum term. The total contribution of the n-digit group is at most 8 times 9 to the n-1 times 1 over 10 to the n-1. That simplifies. 9 to the n-1 divided by 10 to the n-1 is 9/10 to the n-1. So the n-digit group contributes at most 8 times 9/10 to the n-1. Now sum over all groups. We need 8 times the sum from n equals 1 to infinity of 9/10 to the n-1. That is a geometric series. First term is 1, common ratio is 9/10. The formula for a geometric series with ratio less than 1 is first term over 1 minus the ratio. So the sum is 1 over 1 minus 9/10, which is 1 over 1/10, which is 10. 8 times 10 is 80. The entire 9 free harmonic series is less than 80. It is finite. It converges, 3 pages, 1 upper bound, published in 1914, and the question was closed. The series converges, except 80 is a terrible bound. The true value is nearly 4 times smaller. And getting to the true value would take 65 years, and a completely different approach. 2 years after Kempner, Frank Irwin published a follow-up in the same journal. Using a more careful version of the same grouping argument, he narrowed the sum to between 22.4 and 23.3. That was a massive improvement. From somewhere under 80 to a window less than 1 unit wide, and then nothing. For 63 years, people had not forgotten about the series. Computation was the barrier. Direct summation is useless for this problem. If you add up the first million qualifying terms, you get about 7.7. The first billion gets you to roughly 12.4. After 10 to the 24 terms, after adding up more fractions than there are atoms in a million universes, the partial sum is still more than 1 away from the answer. The convergence is spectacularly slow. Each additional digit group contributes a little less, but there are still enormous numbers of qualifying terms, and they add up at a crawl. You cannot brute force this number. In 1979, Robert Baillie found a way around the problem. He wrote a recursive algorithm that groups contributions by the digit structure of the denominator. How many qualifying numbers have exactly 6 digits and start with a 3? What is their combined reciprocal sum? By building the answer layer by layer, digit by digit, he bypassed the convergence entirely. His result, 22.920676619264150348116, 20 exact decimal places. 65 years after Kempner proved the series converges, someone finally knew what it converged to. The work continued. Thomas Schmelzer and Baillie extended the computation to over 100 decimal places in 2008. By 2024, a Maple implementation reached 2,000 digits in about 40 seconds. We know this number extremely well. We can compute as many digits as we want, but there is no expression involving known constants that equals it. No closed form. It is a number that only an algorithm can produce. Here is where the story opens up. Everything I have said about removing digit 9 applies to every other digit. Cross out every denominator containing a 1 instead of a 9. The same counting argument works. 8 times 9 to the n-1 survivors per group. Same geometric bound of 80, same convergence proof. Baillie computed the sum for all 10 single-digit exclusions. Let me read them. Removing digit 0 gives roughly 23.10. Removing digit 1 gives 16.18. Digit 2, 19.26. Digit 3, 20.57. Digit 4, 21.33. Digit 5, 21.83. Digit 6, 22.21. Digit 7, 22.49. Digit 8, 22.73. and removing digit 9 gives our 22.92. Notice the ordering. Removing digit 1 gives the smallest sum by far. Removing digit 9 gives almost the largest. And removing digit 0 gives the largest of all. Why? Because of how often each digit appears as a leading digit. This is Benford's law. Among the positive integers, the digit 1 appears as the leading digit about 30% of the time. That is not a uniform 10%, it is 30%. Digit 2 leads about 17%. And it keeps dropping. Digit 9 leads only about 4.6%. Removing a more common digit strips out more terms. More terms removed means a smaller residual sum. Digit 1 is the most common leading digit, so removing it has the biggest impact, leaving the smallest sum. Digit 9 is the least common, so it has the lightest impact, leaving the largest. Digit 0 is a special case. 0 never appears as a leading digit, so removing it has even less impact than removing 9. That is why 0 gives the largest sum of all, 23.10. But here is what matters. All 10 values land between 16 and 23. They cluster near each other, and they cluster around a specific number, 10 times the natural log of 10, which is approximately 23.03. That clustering is not a coincidence. It is a theorem. In 1916, Frank Irwin asked a sharper version of the question. Instead of removing all numbers that contain a 9, what if you keep only the numbers where 9 appears exactly once? The sum of 1 over n, taken only over integers n where the digit 9 appears exactly one time, also converges. So does exactly twice, exactly 3 times. Every fixed count k gives a convergent series, called the Irwin series with parameter k. Baillie computed these two. For digit 9, the sum over numbers with 0 9s is 22.92. That is the original Kempner series. 1 9 gives 23.04. 2 9s gives 23.03, 3 9s gives 23.026. The values are decreasing. They are falling towards something. In 2008, Bakir Farhi proved what they fall toward. As the count k grows, the sum over numbers with exactly k occurrences of digit 9 converges to 10 times the natural log of 10, 23.02585. And here is what makes this beautiful. The limit does not depend on which digit you choose. Replace 9 with 1, or 5, or 0. The Irwin sums still converge to the same value, 10 ln 10, every time, for every digit. A universal constant sitting behind the entire framework. It gets better. The pattern extends beyond single digits to strings. Instead of excluding a single digit, exclude a multi-digit string. Remove every denominator that contains the string 42. The sum is about 228. Remove 314159. The sum is roughly 2.3 million. And in every case, the sum is approximately 10 to the k times the natural log of 10, where k is the length of the excluded string. Exclude a 1-digit string and the sum is near 23, a 2-digit string near 230. A 6-digit string, near 2.3 million. One formula, 10 to the k times ln 10, governing all of it, 22.92067666192. That is the Kempner constant, the sum of the harmonic series with every 9 removed. We have computed it to 2,000 digits. We know how to compute a million more. We have an exact recursion for every decimal place. We have a universal formula connecting all possible digit exclusions to a single constant, 10 ln 10. What we do not have is a closed form. No combination of pi, e, logarithms, or any other named constant equals this number. No familiar value hides behind it. It is just itself. We also do not know whether it is irrational. It almost certainly is. A rational number would need the decimal expansion to eventually repeat, and 2,000 digits show no sign of that, but no one has proved it. We cannot determine whether the 10 single-digit Kempner sums are algebraically independent. We do not know if any polynomial with integer coefficients relates them to each other. The theory is elegant. It is general. The convergence is perfectly understood. The formula governing all digit exclusions is known, and we can compute the answer to whatever precision we want. But we cannot say what the number is, only what it is near. 1 digit removed from the denominator, and infinity folded into a number we still cannot name.